Let me introduce our partner here, Professor Amit Tandon. We're pleased to have him here today to speak to this class for a number of reasons. Partly because he fits into the curriculum of our semester. So I suppose there's not much I need to say about him. He's a member, a long-time member of the Center for Indian Studies here at UMass Dartmouth. He studied in India and in America, and he now is a professor in the College of Engineering and the School of Marine Science and Technology here at UMass Dartmouth. Dr. Tandon obtained his undergraduate degree in India, and then he came to America for his MS and PhD at Cornell in mechanical engineering. We're excited to learn about his current work. His current focuses are northern Indian Ocean, North Atlantic, Kuroshio, and Brazil current. He is one of the principal scientists of the U.S.-India OMM ASIRI collaboration, and that's what he's going to be speaking about today, I believe. And his interests are about ocean mixing and monsoons. So he's particularly interested in training the next generation of oceanographers in sub-mesoscale oceanography and enjoys tabletop weather in a tank.
So today we are going to talk about monsoons, but before I want to talk about monsoons, I want to talk about something that has been very recently in the news. So in the center I have a paper here which was published in Nature Geoscience, and this was published end of March. So this is very new, this is less than 3 weeks old. And it says long lead predictions of eastern United States hot days from Pacific sea surface temperatures. So the reason I picked this article was because this says something very important about where the memory of the weather systems is, where the memory of long-term memory of weather systems is. So what the study showed was if we are worried about when we might have a heat wave, here is a picture which shows very high temperatures for end of June 2012, and this region here is the region that was suffering from intense heat wave. Had we known this study, we could have made a prediction that this heat wave was coming about 50 days in advance by looking at this pattern which is called the Pacific Extreme Pattern. And here are plotted the sea surface temperatures from about 50 days ago. So I'm showing this to you, which is a news, barely 3 weeks old in the science, just to emphasize the point that the ocean stores a lot of heat and the ocean serves as a memory of the weather system. The weather as we know it, we can predict it a few days in advance. We are actually fairly good on the east coast here predicting what the weather over the next couple of days is going to be. As we go out to a week or 10 days, it gets a bit worse, and that's because in order to predict weather at those time scales, we do need to take into account what is happening in the oceans. So that's the US side of the story. I also wanted to get to the Indian side of the story for those of you who looked at the news recently about what's happening in India. So even though it's, the end of April has not arrived yet, there is a large part of India which is under what are called heat wave conditions. This is a picture from yesterday. And in many of these regions, the daytime temperature is exceeding 115 degrees. So if you thought 90 degrees weather with humidity was worse, think about what it would be like with 115 degrees with high humidity. So already in the last few days, there have been a number of deaths because of this heat wave. So, but the monsoons are still a couple of months away, and it will take some time for the monsoons to occur. So why is this heat wave there, and how soon will the monsoons come? So I'm one of the chief scientists for a joint collaboration between two countries, United States and India. And we are collaborating on making monsoon observations in this part of the Indian Ocean. And this is called Asiri Om. So for those of you who are here taking the science of Kriya Yoga, you're probably very familiar with Om, right? It occurs all the time in many pieces of Indian literature. Here, what we mean by Om is, it's a play on Om, of course, is ocean mixing and monsoons. So our Om has to do with how the ocean mixing plays a role in setting up the monsoons. There are two pieces of monsoons which I'm showing here, and both of them are important. The top picture here is showing you a picture of the atmosphere, the air above the ocean, and the bottom picture here is showing you a representation of the ocean. The air above here is showing the winds during the summer monsoons, and during the summer monsoons the winds mainly come from the southwest going towards the northeast, and over much of India and over much of this northern Indian Ocean. What is shown in bottom here is a state of the ocean in terms of what I call ocean eddies. So where you see these egg-shaped like structures, these are the ocean eddies, and what's being shown here is how high the ocean currents are. So the ocean currents are bigger at the rim of these features, and these features are hundreds of kilometers in their length scale. They're hundreds of kilometers in diameter. So think of an ocean eddy something sort of between here to New York, right? You can, if you were a particle that kind of hangs on and goes around, you probably reach New York in a few weeks, or a couple of weeks, if you were taking a ride in this. So this distance is about 3,000 kilometers, this distance is about 3,000 kilometers, or roughly about 2,000 miles. So we're talking of an area which is about 2,000 miles by 2,000 miles, and it fits a few of these large eddies, which we call mesoscale eddies. So there are a number of collaborators I have here, many from the US, many from India. We have something like 10 US institutions involved in this. UMass Dartmouth is one of them. Some of you may have heard of Woods Hole Oceanographic Institution, which is about an hour east of us. That's one of them. Scripps Institution of Oceanography, which is at University of California, San Diego, is one of them. So there's about 10 US institutions which are part of this team. And similarly, there are about 8 Indian institutions which are part of this team, because we're looking together at how the ocean system sets up and what role does the ocean play in setting up of the monsoons. I should thank both the Indian government for supporting the OM program of India, the Ocean Monsoons and Mixing, and the Office of Naval Research for ASIRI. ASIRI stands for Air-Sea Interactions Research Initiative, which is these are both 5-year programs. This is the 5-year US program, this is the 5-year Indian program, and we are working together to solve this big mystery. So if you look at any part of Indian literature or history or scriptures, all of them make a huge reference to monsoon. I mean, the life on the Indian subcontinent, as you know it, and even the areas around, depends a whole lot on the monsoons. What I'm showing here is a picture of how good we are at modeling what is happening around the ocean. So this picture here shows most of the Pacific, and in the Pacific, our models perform quite well. This is a measure of how good our model is. So think of 0.8 is about 80%, according to some metric, as good as 80%. So in the Pacific, in this blue rectangle, all the models, whether you talk about the Japanese model, the US model, or any other models around the world, Singapore National University model, the Indian model, all of them do a fabulous job of predicting what the rainfall is going to be for June, July, and August, and also other parameters. However, when you go to these areas, when you go to the northern Indian Ocean or this part of the Western Pacific, all the models are miserable. Actually, none of the models have any significant degree of skill. What that means is that we cannot really predict what the ocean weather conditions are going to be like in this region. So that affects the safety of the ships at sea, that affects the whole cargo that passes through this region, that affects, if you remember, a lot of the oil comes through here. That affects all of the trade that's going on in terms of the ships. That also affects the safety of Navy ships that are flying in this region. And that also affects the wave forecast we have over the ocean. And then the inaccuracy that we have in the weather in this region affects our weather forecasts about 2 weeks later on because of the global teleconnections. So something that is happening in the Pacific right now, or something that is happening over the northern Indian Ocean right now, will affect how our weather is going to behave about 2 to 3 weeks from now. So if we are interested in making our weather forecasts more accurate over 2 to 3 week time scale or longer time scale, then we can't just look at the ocean in our neighborhood. We have to go globally and look at what is happening in the Indian Ocean. And it turns out that the reason the models do so miserably here is because we don't quite understand how the upper ocean talks to the lower atmosphere. So we need to understand how a communication happens between the upper ocean with the lower part of the atmosphere. And if we can do that better, we'll be able to do better prediction of tropical storms. That will save a lot of lives, as well as do a better prediction of monsoons and better prediction of where our weather is going, what our weather is going to be like 2 to 3 weeks from now. So let me just talk about a little bit about this region. So what I've done here is plotted population on the y-axis of population per unit longitude, and longitude on this axis. So if you look at the North and South America, for instance, this represents the population in North America and South America. This is where we are. This represents the population over African and much of the European continent. And this shows us the population over the Indian subcontinent and China. So those are the big peaks. If you look at this area, this circle around here, there's about 1.5 billion people who live here, and they depend on monsoons for their water, food, and economy. When we look at monsoon pictures, they often look like this because a strong monsoonal event or an active event may flood the streets and bring lots of water. But these monsoons are also made up of break cycles. These are times when it doesn't rain at all or rains very little. So let's look at a representation of that. So in here I'm showing you a summer monsoon picture. Again, the winds are coming from the southwest going to the northeast, and much of this region in India, central India, gets most of its rain during the summer monsoons. This would be a typical picture you would see in your geography textbooks in sort of grade 6, 7, and 8. This is a winter monsoon, so the winds completely change direction. Now they are coming from the northeast, going towards the southwest. And South India and Sri Lanka gets most of its rain during winter monsoon. So this may be more like December, January, and February. And summer monsoon is more like June, July, and August. So the monsoon picture looks at, people think of monsoon as something that begins in June, goes on until almost end of September. And this thin curve here shows you what an average monsoon rainfall looks like. The real rainfall, however, which has been added up for central India, is shown in these black towers. So some of these biggest black towers are when you get the biggest rainfall events, and they are followed by events where you see much less rain or hardly any rain, and then you get another big black tower, which is another major rain event. So monsoon is not one continuous phenomenon. It's made up of big times, huge rainfall concentrated in very short periods of time, and then that dies out, and then maybe the next major rain event will come about a week or 10 days later, and then that dies out, and so on. And so a whole lot of agriculture depends on whether we can accurately predict when the next big rain event is going to be, because then farmers and everything else, everybody would plan according to that. And when the next dry event is going to be, or break cycle is going to be. So it turns out that, again, none of Ball's models, doesn't matter which coupled ocean model you take, it doesn't matter which country you take it, none of them can actually make any sort of useful prediction of the active and break cycle. They can say something about whether a particular monsoon season is going to be below average, average, or above average, and they have some skill in that, but again, that is very low skill. So just for reference, the early monsoon predictions for India are that this year is going to be normal to above normal monsoon, about 106% of normal. When we go above 110%, that becomes excessive. That's called excessive. And when we go below 90%, that's drought. So only a 10% difference in the seasonal rainfall makes a difference going from drought year to flood year. So why Bay of Bengal? This is a region which is a very anomalous ocean. So what is plotted here is what is called surface salinity. So think of this as how much salt there is in the ocean, in the upper ocean, at the surface of the ocean. So this part here, which is the Arabian Sea, is very, very salty, and this part here, which is Bay of Bengal, is very fresh. And it is very fresh both because it gets lots of rain and also because it has some major river outflows. So there's a major river here, Irrawaddy, there's the Ganga Brahmaputra basin here, there are other rivers here that flow out of the east coast of India, Godavari and others. So this basin is very fresh. What that means is when you have fresh water over salty water, the fresh water is usually lighter and it floats on top of the salty water. So that leads to a layering. And so you'll hear me use the word stratified, which basically means that there are layers upon layers of the ocean where you have relatively fresh water up above and saltier water below. And so when you have a situation like that, that makes the surface, it's easier to warm the surface when you have fresh water floating on top of salty water. And so the sea surface temperature responds rather quickly. It can warm up quickly, it can communicate with the atmosphere in ways which are very different from the way it does here. And that has implications for ocean life as well. Here's another picture of the northern Indian Ocean. Again, here I'm showing you the surface salt content here and here, much saltier on the Arabian seaside, fresh on this side. And what this is showing are the major rain event systems. Most of the major rain event systems actually take place in this northern Indian Ocean. There are a few in the Arabian Sea, but most of them are in the northern Indian Ocean, the Bay of Bengal. And this goes back to low pressure systems from daily satellite analysis for the past 30 years. And all the big systems have virtually taken place here. So this is the region that US and Indian scientists concentrated on more. I just wanted to show you a comparison between three major oceans. So I've chosen the North Atlantic, which is shown here, the Northern Indian Ocean or Bay of Bengal, which is shown here, and the Pacific, which is shown here. So this is showing, here I'm just showing you what the surface salinity or surface saltiness looks like. So, and again, as you can see, the Arabian Sea is much saltier compared to the Bay of Bengal. In fact, Bay of Bengal is, along with a few other places, is one of the freshest parts of the world ocean. What is the other interesting part is when we look at it in terms of how it varies with depth. So here I'm going from about 8 north to 20 north. So this is the southern end to the northern end. There is much fresher water in the Bay of Bengal, and it's also much shallower. So this depth here is barely about 20 to 30 meters, whereas in Atlantic and Pacific, this water depth goes much deeper. So I had a seasonal movie of this just to show you how it varies from month to month. But the main thing to remember here is that as we go through summer monsoons, this layer is actually quite thin. And what this average picture doesn't show you is how does this actually vary with the monsoons. And this is what we measure with our ships. When we use the models, they also tell us, so again, this region we are considering is about 3,000 kilometers by 3,000 kilometers. When we look at the surface saltiness from the satellites, we get a picture which looks like this, so very pixelated. But even this is telling us that there's more fresh water here and more salty water here. When we run our models, we can see that some of these models are giving rise to eddies, but these models cannot capture what is happening with smaller scales. So when I say scale, I mean we want to know what is happening at 3,000 kilometers, but in order to predict how the ocean and atmosphere talk to each other, we have to go down smaller and smaller. We have to be able to zoom in and figure out how these two talk to each other. So what I've told you so far is that there are very serious errors in simulating all aspects of the monsoon. All the models get this wrong. The modeled upper ocean mix layers are too deep and too cold compared to the real ocean. So then they don't rain in the right place and they cannot be used for predicting when we are going to get the rain. There is day and night variability, there is within the season variability, which is very important, but again, it's not captured by our models. So why are our models bad, and how do we improve them? How can we improve them? So to improve them, we need to figure out how air and sea communicate with each other, how the upper ocean and the lower atmosphere talk to each other on various time scales by studying that further, because that's not well known. And we also need to think about how the ocean here responds differently than other parts of the world. Because our models right now, they are treating the ocean in the northern Indian Ocean just like they treat Atlantic or Pacific or any other ocean. But there are some very unique processes happening here which are not well understood. So in order to actually figure out what's going on, we decided that both our countries will put some resources and invest our time and time of lots of young scientists and older scientists like me here to actually figure out what is happening in the ocean. And there are many challenges because there are some geopolitical challenges in this region. Port calls are very difficult for arrange for foreign vessels in a different country, but we've been able to do that now for a big US global research vessel. There are multiple ministries in India that we had to work with in order to make these projects happen. So that includes the Ministry of Earth Sciences, that includes the Ministry of Home Affairs, that includes the Ministry of External Affairs, that also includes, I guess, we had to get some defense clearances and Coast Guard and so on. So that makes it a tough thing to do. And there were constraints on where we could go and work. But we were able to make a lot of progress through realizing that we have common interests, both as India for obviously its the relevance of monsoons to India, and US because of the relevance of global conditions, global weather conditions, and how it affects us. So we worked by recognizing our common interests, communicated very frequently. We spent a couple of years building trust and collaborative ties by holding workshops, both workshops in India and workshops in the US. We developed science plans for both countries, and this was done by scientists communicating with each other. We networked a lot with different ministries so that they could support us. We had 20-day training workshops in India where US scientists went and trained young scientists over there along with senior Indian scientists. We had Indian team on the US ship and the US team on the Indian ship as well. So this ship that you see from sort of front to back, in the background is the Indian ship, and there are some US scientists here along with Indian scientists who were on our ship last August, September. So this is taken from the US ship on which I was a co-chief scientist, and the Indian ship here is in the background. So both these ships are about 100 meters or about 300 feet long. So these are quite big ships. They can carry a crew of about 30 people and about 25 to 30 scientists. And there was a lot of training and advanced tools going on both the ships. So there's a glider that is shown here. There's another Lagrangian float that is shown here. We use lots of different kinds of instruments. So let me just quickly tell you about the themes. So there are 8 institutions in India, as I mentioned. These include the National Institution of Oceanography, which is Goa, a Space Application Center that's funded by the Space Ministry, and then National Institute of Ocean Technology in Chennai, and IIT Madras, IIT Bhubaneswar, National Institute of Oceanography in Vizag, Indian National Center for Ocean Information Studies, and Tata Institute of Fundamental Research. So we have scientists, the Indian scientists are from these institutions, and there's about 30 senior scientists plus the students who are in their groups collaborating. So we got started in 2010. I won't go through this entire list. Just wanted to say that anything that you see in yellow were efforts that were happening in India. Anything you see in white were efforts that were happening in the US. And so I was a part of this, part of leading this right from 2010, and it's now 2016. So here are some pictures. There is some training going on on the US ship here. We all have to wear hard hats, of course, when we're working outside on the deck, because there are some pretty heavy things that can go wrong. Here we have an Indian junior scientist and a junior US scientist that are working together to make this kayak. I'd like to show you what this kayak is. This kayak, it turns out, is as powerful as a ship. So the ship is very expensive. A ship costs about more than upwards of $100,000 a day to operate. So when we get, as scientists, when we get about 15 days or 20 days of ship time, we consider ourselves very, very lucky, because we have a big resource on our hands to do these studies. So it turns out that you can make this kayak and instrument it so that it becomes almost as powerful as a ship. So think of it this way. For some small amount of investment, you can make measurements from this that equal about the same investment you make in a ship, which is upwards of $100,000 a day. And when I say 100K a day, I'm not including the salary of the ship's captain and all the crew that goes with it, and the time of all the scientists. I'm just mainly talking about the investments you make in the hardware. So we had a number of classes as well, and this is my favorite weather and tank experiment that I carried to India to make some to do some experiments there to explain concepts. So the biggest cruise that we have is August, September 2015. And this was a cruise that I was out for 2 months last year. And we had about 35 days of ship time. So that's unheard of. And we were very happy that we had that much ship time on the US ship, which is called Research Vessel Revel. And the Indian ship, which is called Sagar Niti, which stands for Niti basically is a treasure, so it's the treasure of the ocean. And in order to study this northern Indian Ocean, we had to study it from very large scales, in the sense of what is happening over thousands of kilometers to what is happening over a few kilometers, 1 or 2 kilometers. And so we use many different kinds of instruments. And so I'm just showing you some pictures that we gather from these instruments. So this picture here is taken by making lots of profiles from the ship. So this has something like maybe 800 profiles in these 1,500 kilometers. One profile every 2 or 3 kilometers. And this is showing you the top 250 meters. And what this is showing is, again, very fresh water here, salty water here, very shallow mixed layers. This is showing you what the structure looks like over 300 kilometer scale, where we see a big ocean eddy that goes as deep as 150 meters. Then we see here 24 kilometers, we're seeing some ocean frontal structures that we are modeling in my lab. And then further down, we see something that actually looks like what's called an open ocean bore. These are the kinds of things we actually see at the river mouths, not 300 nautical miles away from this, from the border, from land. So we also saw these kinds of physics animals, so these kind of physical animals, very unique to this part of the world. So how did we make these measurements? We used many instruments, and I'd like to see if I can show you something about these instruments. So some of them look like underwater planes. These are called gliders. These can go on for thousands of kilometers. It takes them months to do that, but they slowly gather data as they go along. And as I said, taking measurements from ships is very expensive, so we use these kind of airplanes, or underwater airplanes, underwater water planes, I guess, gliders. Then we use instruments like these, which are called floats, that have some capability to send us data in near real time using satellites. We also use drifters, which passively drift on the surface of the ocean and taking data and then sending us data back. We use moorings, and this is a mooring which is deployed by Woods Hole Oceanography Institution. Costs about $1 million, because what it gives in terms of data is absolutely worth it, because there is no other way to get this data to be able to make predictions. this mooring is great at telling us how the atmosphere and the ocean talk to each other, because it has instrumentation going all the way to the ocean bottom. It is very heavily instrumented in the upper ocean and also the parts that are sticking out in the atmosphere. So it can really tell us, much better how the ocean and atmosphere talk. We also use more short-term vehicles like turbulence gliders and AUVs. And then there are other things which are actually driven by surface waves. So we deploy these surface wire walkers, we leave them out for weeks at a time, and then we are ready to go home. We pick them up and we see the data from them. So these things that I showed you are things we just kind of deploy into the water and let it drift. We also have lots of instrumentation on the ships that makes measurements. So let me show you what we did together. So on the left-hand side here is the US ship. This is Roger Revell, the global vessel I was talking about. And here's the Indian ship, which is Sagar Nidhi, and then here's Sagar Nidhi and he is Revell. And I'm showing you a Google map picture of this. We are in the open ocean, so there's no land anywhere nearby. But you will see one of these is the US ship, the other one is the Indian ship. And so you will see what we do as we go along in this movie. So right now we're just surveying the ocean to figure out what the surface conditions are like and what subsurface conditions are like. Here is this wave buoy we had deployed some time ago. Now this Roger Revell, the US ship, begins to deploy lots of drifters in clusters. Some of them can measure surface salinity, some of them can measure both surface salinity and temperature. And then we deploy these other things called wire walkers, and now the two ships are separated by a few kilometers, and they begin coordinated exercises. So at the time there was a large eddy here in this part of the Bay of Bengal. And so we are trying to sample what is happening at the edge of this eddy, because that's where most of the interesting physics is. In between here you will also see a third ship come out. That was the little kayak I told you about. So right now we are going across this surface patch back and forth to study what processes are going on. At the same time, we are making measurements on both the ships so we can understand how the ocean and atmosphere talk to each other in this part of the world. All these assets that we have deployed are basically going around and telling us where the eddy is and making measurements of the eddies that go along. Here's the third ship. This is the kayak that goes along with us for almost two of these up and downs. And each one of these legs took us about 7 hours to do. So on the ship, the work never stops. You're basically working in 12-hour shifts. So I was working 3 a.m. to 3 p.m. Other scientists would be working 3 p.m. to 3 a.m. And we would be continuously working because the ship time is so expensive. So there was always somebody or the other continuously making measurements. There's another experiment we are doing where we've deployed a drifter and then we're making measurements around this. So this was a very, very successful ship experiment. There were many firsts that were achieved during this time. And so I'll just go through quickly what we did. This is the first ever international collaboration between two ship parallel tracks, US and India. This is the first deployment of what we call ROS. This is the kayak, and I'll show you a movie of the kayak equipped runs. This is first ever 3 platform parallel sections, first ever 3 ships working together, and then the third ship is the kayak. This was the first 3-meter float deployment in the Bay of Bengal. We took more than 10,000 profiles of what is happening in the ocean. So the ocean was mapped in a way in northern Indian Ocean that has never been done before. We have largest number of current meters that were deployed, the largest amount of current that have ever been observed in this part of the world. And we also deployed gliders. These were the underwater airplanes, what I was calling underwater airplanes. And then there was training conducted for the first Indian glider deployment. We released 51 drifters, and this is again, and we got unprecedented amount of high quality data. So I'm standing here on the ship looking very happy. Here is a picture of the Indian ship against this kayak Ross. So let me see if I can show you a little GoPro from the Ross. So what you're going to observe here is we are on the ship here. We are going to deploy Ross from the back of the ship, and then we're going to let go. And the camera on the Ross will show you how it behaves. So I'm not showing you the instrumentation of the ROS, but I thought it would be kind of fun for you to see how this looks. It backs off, and then, or rather, Revel is going forward and ROS is not, and then ROS turns. And so when it's close to the ship, we are just telling it where to go, and then after it goes above beyond our range, then we tell it using satellite signals. So there's nobody on the ROS, but just the GoPro, which is recording how ROS is doing. Here's another picture. Revel, you can see Revel in the distance. And now this is a picture from Revel taken off the ROS. The yellow boat happily going and doing its job. We tell it, you know, from what point to what point it should go and what measurements it needs to take. So as a result of all of this work, we now have about 1 year communication between atmosphere and the ocean almost at 15-minute intervals. Actually, we take the data less than every minute or so, but then we average it. The portion that the models think is right is shown in black. The portion that is actually measured is shown in red. So in many places, black and red agree with each other, but there are big places where black and red disagree. So we are doing a lot of work to figure out why is it that our models cannot capture these events that are going on in the picture. There are many science findings from this. I'm only going to concentrate on one of them. So there, you know, I divided them into 5, but I thought maybe just talk about one of them, because in the beginning of the talk I talked about the memory of the system, memory of the weather system resides in the ocean. So here the memory of the system is residing in big pools of warm water which are subsurface. Now normally warm water would be lighter, so it would come up. Here warm water does not come up because it is overlaid by fresh water which is even lighter, the river water and the rainwater. So what we did was we were able to map a lot of these large pools of subsurface waters, and it showed us that a lot of these warm pools are actually captured by eddies. So here I'm showing you a model picture of what these eddies look like. So these eddies do have some high pressure and low pressure systems. They do bulge up and down. And the biggest difference from this highest bulge to the lowest bulge is only about 30 centimeters or so. But our satellites are so good that we can actually figure out what this bulge difference is. And so we incorporate some of that. So this is showing you in June 2014 what the bulges look like. So here is what we call a cyclone. Here is an anticyclone. And what these eddies do, these are the eddies that I was showing you in the beginning of the talk. These eddies basically stir in this fresh water from the rivers into the salty water, making these very interesting patterns. But these interesting patterns then have a huge impact on what the weather is doing. So that was modeled. This is data. This is actual observations. Our observations, which here I'm showing you over a 4,000 kilometer transect, showed that there were lots of places where huge amounts of warm water is actually trapped. And this huge amount of warm water, this heat, which can serve as an energy release, can be released if an intense storm develops or an intense hurricane develops. So the eddies are actually acting as a subsurface warm water memory bank, and these can intensify the monsoon storms. So this is why when you saw 30 years worth of data and you saw all these storms that are taking birth in the northern Bay of Bengal, that is happening because that is the region where most of the heat is getting trapped subsurface, and then when the right moment comes, it gets released and it intensifies the monsoon storms. So I'll pass over the other results, but if you're interested, we can talk more about it. So essentially, this 5-year collaboration, which is still ongoing, on the Indian side, the funding ends in March 2018. On the US side, the funding ends in end of 2017. So what we've done is we've established a long-term observatory to figure out how the air and sea, how the atmosphere and the upper ocean talk to each other, figure out how much solar input is coming in, testing the formulae that we use in the model so we can actually improve them in the longer term, looking at what the upper ocean structure looks like, figuring out how the ocean mixes this fresh water that you see on the top, because that's critical to how much heat is going to get trapped. We are testing and improving our models. And what my lab is doing a lot of this process modeling, trying to figure out at smaller scales how to understand this, both the ocean atmosphere communication and how this heat gets trapped. Now I'd like to tell you a little story. So this is the IST part of my talk. There is a story which is about Samudra Manthan. Samudra stands for the ocean, and Manthan is basically churning of the ocean. So what I'm showing you here are two reliefs. These are both from the Hindu temples in Angkor Wat in Cambodia. And here is a sculpture which is at the Suvarnabhumi airport in Bangkok. What all of these are showing is, on one side are the devas or the demigods, and on the other side are the asuras or the sort of bad people, the good and the bad. Essentially, it's a long story, but it's, you know, like all good mythology stories, it talks about the victory of good over evil, but it does in a very interesting way. So what they're churning with here is a mountain, which is shown here, and this is I forget the name of the mountain, but I think in the south it's called Meru. And they're using the snake whose name is Vasuki, who's the snake that's associated with Lord Shiva, and they're churning the ocean. Now, when they started churning the ocean, the story goes that they very quickly figured out that they needed some kind of support. So they asked. So it turns out that Vishnu has 10 avatars, and one of his avatars is to come as a tortoise. So he comes in as a tortoise and he goes inside the shell, and so they use his shell for support to mount the mountain, and then they churn it like this, and then you have suras on one side and asuras on one side. And so the story goes that as this churning is going on, a lot of things come out of the ocean. Some things are like jewels, and they are the Kamdhenu cow, which can give you anything you need, etc. And some of them, and one of them is actually poison, the most poisonous poison mankind has ever known, or eternity has ever known, which is called halal. So it turns out that when that poison is coming out, it's going to destroy the entire universe, and then Lord Shiva comes and he takes it in so that it doesn't destroy the universe. And then his wife grabs onto his neck so it doesn't go deeper than his neck, so he has a blue neck, and that's why he's called Neelkanta. So there are many stories connected to this story. But ultimately, what comes out of this is Amrita, or the nectar of life, which is supposed to give us eternal bliss. So you might be wondering, this seems like a fairly complicated story to describe good over evil. And it turns out that there is a lot of symbolism in the story if you actually think about it. So the suras and asuras actually are supposed to be the good and the bad within us. So each of us have some good properties and the bad properties. And it's the conflict of the good and bad that is done with the snake. The snake basically stands for the desires that we all go through. And so the desires make this churning happen, and what comes out of the desires can be both good and bad, halal as well as the amrit. But when it comes out, if we are careful and if we don't get distracted by the sidelines, and if we concentrate, so the pole stands for whatever, the mountain stands for the concentration, and the tortoise actually stands for you have to withdraw from your senses in order to concentrate. And so if you concentrate, you get to the eternal bliss. And so I just showed you a picture of what the devas on the right here look like at this airport sculpture of this famous story. So the ocean is supposed to be the human consciousness whose churning leads to us going different experiences. The snake is the desires, and the devas and asuras are the good and the bad within us. The mountain which is used to churn the ocean is our concentration, which can be negatively affected, so we need to withdraw from our senses like the turtle into the shell and support our concentration. The poison that Shiva drank, halal, is our pain and suffering, and the jewels that come out of the ocean are like materialistic pleasures which are not supposed to distract us. So for me, this churning of the ocean, what that represents is that if you work hard and try to get the knowledge out of it, then the pursuit of Amrita is the pursuit of the knowledge to basically get to the eternal bliss or Paramanand, which I'm sure Kriya Yoga talks about. So here is my last slide. So when we would work from 3 a.m. to 3 p.m., after 3 p.m., at 4 p.m. we would be ready for our dinner. So between 3 p.m. and 4 p.m. on the US ship at least, for those of us who were coming off ship, was the time to do some yoga. So here we have some young scientists, myself, a crew member, and another member of the science party. We are getting ready to do yoga on the deck of a ship. And it's a very tough place to do yoga on, but we have a lot of fun doing it every day. So here is just one set of photographs from our yoga session on the deck of the ship. Nothing quite like it. All right, thank you.
Time for questions.
Yes, take it.
Thank you very much for the nice presentation. I think there is a lot of work you guys did, so appreciate. I was just wondering if you guys collaborated both with the Indian group there, and you find them to have been equipped with some of the meteorological data that they have collected over the years that you could share and do some predictions for the monsoon there, short term or long term.
So most of the meteorological data that India collects is done over land. So there is some data that happens. India has put out some ocean moorings, so they get some limited amount of data there, and that data does go into the Indian Meteorological Department models. However, as I showed you, the ocean is about 3,000 kilometers by 3,000 kilometers, and what you have is about 5 or 6 places that you make the measures. Sorry?
And you are measuring the things in the wrong place also on the land, or the ocean is the one.
No, so you do need to measure what the conditions are like on the land, but you also need to measure what the conditions are like in the ocean. So we have, so India has put a lot of investment in remote sensing, so they have a very nice satellite system. Some of that makes it into the models and some of it doesn't. They have a mooring network, a mature mooring network. What they did not have before we got started was the ability to put out these kind of floats that I was talking about, because what you want to do is, let's say a hurricane is coming or a tropical storm is developing, you actually want to get the data where the hurricane is, and you may or may not have a mooring there. So if you train yourself well, then you can drop an instrument that can make oceanographic measurements there, like a float. Or if you have enough gliders, then you could be running gliders back and forth, and then you can, if you know that a particular storm is coming, then you can direct your glider to sort of slowly make its way in that direction. So that is a capability they did not have. So that's part of, as part of this project, they have developed that capability now. Am I answering your question?
Yeah, go ahead. And are any help with the predictions? Do you have anything?
So let me just back up a bit. Until about 2 years ago, any prediction that was done in India for monsoon forecast was done purely on the basis of statistics. What that means is that they would say, oh, the rainfall in India depends on some conditions in Sahel and Africa, some other metrics, and they were essentially doing a curve fitting. It did not involve any dynamics. It did not involve any Newton's laws or fluid mechanics or heat transfer, any of those concepts that you and I know about. Only in the last 2 years have they started using the dynamical model. And then there was a good reason, because when they saw these coupled models from all over the world, they didn't seem very good at making these predictions, so why should they use them, right? So now for the last couple of years, they're using both the statistical model and the dynamical model for predictions. So if you go now to IMD website or IITM website, you will see that they're using both these models. But these models are still deficient. So I don't mean to say that these models should not be used for prediction, because they do have some amount of truth in them. But they're still deficient. So the work that we're doing now, the work that we will end by 2018, it will take about 5 to 10 years, about a decade, to make it into operational models. That's the scale at which things go, because right now we've collected the data, we're trying to understand the data. By the time our students and their scientists and their students work on it, and then we write up these results and publish these results, and then we say, okay, here's the essence of what we want, here's how we want to improve the models, then we first have to test the models, and then if the models are performing better, then we have to put it into operational prediction. So what we're doing now is actually sowing the seed for what is going to happen 5 years from now and 10 years from now. So if you look at, nowadays everybody talks of El Nino, right? We have become so confident about when the El Nino is around, how that's affecting the weather in California, how there's a drought condition in California, and how we're expecting that to get better as the El Nino goes away and gives rise to La Nina condition. If you go back 25 years ago and look at the literature, nobody understood what El Nino was or what La Nina was and how these affected. The reason we understand El Nino so well now is because we have a bunch of moorings along the Pacific, in the equatorial Pacific, and we've been now studying that phenomena for, so first we studied it for 10, 15 years, and now we've been studying it for more than 25 years. So this is the, if this work can continue, then this has the potential to do for India and Asia what the Pacific work did for El Nino and La Nina. And ultimately, what is happening in the northern Indian Ocean is connected over a 2-week time scale to what is happening in the Pacific and the Atlantic. So if we are truly a global family, I forget what is it called, the Vasudhaiva Kutumbakam, yes, that's the thing I was looking for. So that's one of the things that you might want to introduce to Kriya Yoga students. So there is a very ancient saying which goes Vasudhaiva Kutumbakam, which says the earth is but one family, which basically means that the earth is one family. That fits directly into the Gaia ecology concept, right? So if the earth is one family, then we have to understand the earth as a whole. So we can't just understand only the Pacific or only the Atlantic. We have to understand what is happening in the Pacific, the Atlantic, and the Indian Ocean, because together these are more than 75% of the Earth's surface. Right.
Any other question? Amit, I have a two-part question.
Sure.
Monsoon is an annual event.
Yes.
But the heat that is trapped can affect subsequent monsoons. Is that what you said?
So the heat the heat that got trapped, the heat that is getting trapped now, or the heat that got trapped at the end of the last monsoon season, would affect the January-February monsoon. Some of that heat will hang around long enough to affect the subsequent tropical storms this year as well. Because so the river water as well as the heat can stay around for months churning in the bay. And I think, if there is sort of one take-home message that we got out of these 5 years, that's the biggest message. And what we have is we now understand the scales at which this heat is getting trapped, both in the vertical and in the horizontal.
I know you just said that it will take a while to process all this data and make a model, but just can you give us some idea of how climate change might affect monsoon in the subcontinent?
So that's a tough question to answer, because if you don't even understand the basics of where the monsoon is, how can I talk about change of something that I don't even understand some of the basics? That being said, there are modelers who've looked at how the monsoons would behave in these imperfect models that we have. And what they find is, and they've also looked at the rainfall data that's been collected. So India has had rainfall data since 1750s or early 1800s. And so they've also looked at the rainfall data going back, the reliable rainfall data over land. What they find is that the rain events have gotten more intense, but also shorter in duration. So they are higher in intensity, but in general they are a bit shorter in duration. If that is correct, then what that does is that once the rain falls, it leaves the soil more quickly, right? And when it leaves the soil, when it goes through the soil quickly, it also takes some of the topsoil with it. Because if you have a more intense rainfall, that will lead to more intense floods. So that is a bit worrisome. And that is worrisome because if the rainfall events are bigger and we are not able to capture the rain, that is, if it makes its way into the ocean too quickly, that's bad because you're not using the fresh water that you could. And secondly, if it's taking the topsoil with it, then that's not very good for agriculture either. So I think those two trends are very strong. If you combine that with deforestation and poor water management, that gets even. But that's now going into your territory.
Any other question for Amit? Thank you, Amit.